Flipped Classroom video for Maths AS Unit 1, Introductory Proofs. So we're going to look at some proofs and with them introduce some useful ideas and techniques. So the first thing we're going to consider is it true that the sum of three consecutive natural numbers is divisible by 3? So we could first, in looking at something like this, have a go. Just try a few numbers. So if we do 1 plus 2 plus 3, we get 6, which is 3 times 2. So that is divisible by 3. 4 plus 5 plus 6 is 15. Again, 3 5s divisible by 3. And the same happens with 12, 13 and 14, and with some bigger numbers. So this suggests that the claim might be true, but it doesn't prove it. In order to prove it, we have to do some proper maths. So, theorem. The sum of three consecutive natural numbers is divisible by 3? Question mark. Now really this isn't yet a theorem, but as it happens this one is true, so I'm allowing myself to call it a theorem. So how can we prove it? Well, the first thing is we are going to generalize. So instead of using particular numbers, we're going to say let the numbers be n plus 1, which is the next consecutive number, and n plus 2, which is the following consecutive number. So those are our three consecutive numbers. If we add them together, we get n plus 1 plus n plus 2. And if we tidy that up, we've got three n's in there, so that's 3n. We've got a 1 and a 2, so that's plus 3. And now we can factorize that into 3 times n plus 1. Now that means the sum of those three numbers is 3 times something, and that means it's divisible by 3. So we've proven it, and it's called a proof by deduction. And deduction is where we derive from something we know by means of reasoning. Okay, let's have a look at another one. Now, this follows on from the previous one. The sum of 4 consecutive natural numbers is divisible by 4. Now, you'll notice I've now called this a hypothesis. And that is because, as I hinted at before, we don't have a theorem until it's been proven. So at the moment it's a hypothesis. It's something we're putting forward as a possibility. Let's try a few numbers. Oh dear, the first numbers we tried don't work. 1 plus 2 plus 3 plus 4 is 10, which is 4 times 2.5, and divisible means it would have to be 4 times a whole number, and it isn't. So what we have here is something which has disproved the hypothesis, and this is called disproof by counterexample. Now we could do this in an algebraic way, so in the same way as we started before, we're starting with n and then the next three numbers, so we've got 4 consecutive natural numbers, and when we tidy that up it comes to 4n plus 6. Now that is 4 times n plus 1, but then we've got an extra 2, and that in fact is never going to be divisible by 4. So this is very false. Now we have this, a statement. The sum of 5 consecutive natural numbers is divisible by 5. And the word statement is an alternative to hypothesis. We're just stating something to see if we can find out if it's true. Strictly speaking, we perhaps should have a question mark at the end of that sentence. Now, as before, we'll try a few, and starting at 1 works, starting at 4 works, starting at 12 works, so it's looking good. But as before, it doesn't matter how many particular examples we would show were true, that doesn't prove the theorem or the statement. So let's have a go at doing it algebraically. So there are our 5 consecutive numbers, and they add up to 5n plus 10, which is 5 times n plus 2, and therefore the sum is divisible by 5. Now there is a little trick that we sometimes use, which I'll show you here. So this is to illustrate that we don't have to start at n. We can start with a different number. We can put n in the middle, as I have done here, and the reason for this is that when we add them up we actually get 5n. And this is quite nice because it shows sort of the structure of what's going on. The reason this works is that the middle number then has numbers either side where the add 1 take away 1, add 2 take away 2 cancel each other out, and we can see nicely then that it is 5 times n. And you might want to think about the fact that it worked for 3, it didn't work for 4, it works for 5 in relation to this purple example of a proof. So the statement is now proven and we can turn it into a theorem. And again we've got proof by deduction. So another one, hypothesis. If p is a prime number, then 2p plus 1 is also a prime number. Okay, we'll do what we did before, we'll try some out. This time I'm making it into a little table. So we start with the first prime number is 2, and when we put it into the 2p plus 1 formula, we do indeed get another prime number. And for 3 we do. And for 5, so this is looking good. But for 7 it doesn't work. 2 7s plus 1 is 15, that's a composite number, it's 3 times 5, therefore not a prime number. This does give us a chance to have a look at another idea. We've disproven that one by counterexample, but what we could do is say if p is a prime number less than 6, then 2p plus 1 is a prime number, and we can see that that is true, and the proof would be in just listing those sums we've done up here. Okay, so that's called a proof by exhaustion. We have exhausted all the possible cases. Because we were talking about prime numbers less than 6, those are 2, 3 and 5 only. So if we test them against the statement or the hypothesis, then if they're true, then our theorem is true. So here's another one. If p is a prime number, then p to the power of 10 minus p is never a prime number. Now for the proof of this one, we can take a factor of p out of that statement, p to the power of 10 minus p, which gives us p times p to the 9 minus 1, and actually in one line we've proven it, because that is a composite number. So this has two factors, therefore is not prime, and another proof by deduction. Okay, so let's have a look at n cubed minus n. If n is a natural number, n cubed minus n is a multiple of 3. So what might we do with this? Well, because we're talking about multiples, a good move would be to factorise, and we can see we have a factor of n. Then you may recognise that we have n squared minus 1, which is actually n squared minus 1 squared, and we have the classic difference of two squares, which means we can factorise that to n times n plus 1 times n minus 1. And if we now rearrange those so that we have them in order, we've got 3 consecutive numbers. Now, if we look at different 3 consecutive numbers, then we can see that one of them is always going to be a multiple of 3. That's to some extent how you start learning about times tables: 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. And we could do some more writing down to show that this is the case, but at this point in your maths we would allow you to just say, yeah, in any consecutive 3 numbers one of them is a multiple of 3. And because one of those factors of n cubed minus n is therefore a multiple of 3, then n cubed minus n is a multiple of 3. So again, proof by deduction. Now, it's natural to have a look at, if n cubed minus n is a multiple of 3, will n to the 4 minus n be a multiple of 4? And let's have a look. So, is this a proof? Question mark. So again, we factorise like we did before. Now this next line, you might have to just check with a pencil and paper. Hopefully you've got a pencil and paper when you're watching any of these videos and you're making notes. But anyway, it happens that n cubed minus n factorises in this way. Now at this point we have to use another sort of trick, because we've got 3 factors and it's not immediately obvious whether we have a multiple of 4 involved in them, or 2 factors of 2. That would show us we had a multiple of 4 as well. So what we're going to do is look at cases. We're going to look at when n is odd or when n is even. So when n is odd, then n minus 1 must be even, and when n is even, n minus 1 must be odd. So there's our factorisation of n to the 4 minus n, and if n is odd, we then have n minus 1 is even. If n is odd, n squared will be odd, so in that last bracket we've got an odd number plus an odd number plus another odd number, which we know is odd. If n is even, then n minus 1 is odd, and then we have n squared plus n plus 1 is even plus odd, which is also odd. So this tells us that because we're looking for a multiple of 4, that would mean we need 2 factors of 2, which I mentioned a minute ago. But since we only have 1 even factor, this will not always be the case, so the hypothesis is false. So what's happened here is that we have actually disproven this by deduction. We've done some logical steps and we've deduced that it's false. A couple of little things to point out at the end here is, a bit like with 3 consecutive numbers including a multiple of 3, for a full proof we might want to show that odd plus odd plus odd is odd, but again we assume that by this stage in your mathematics you would be able to show that, and it's a reasonable basic fact to use within a proof. The other thing about this final one is that in fact if either n or n minus 1 were itself a multiple of 4, then we've shown that n to the 4 minus n would be a multiple of 4. So just as before we did a proof by exhaustion example by doing some cases and then restricting the statement to, in that case, primes less than 6, I think it was. In this case what we could say is that if n is a natural number where either n is a multiple of 4 or n minus 1 is a multiple of 4, then n to the 4 minus n will be a multiple of 4. And then we could use what we've written as a way of proving, with a bit of modification, that was a correct theorem. So we would be restricting the values of n that we were claiming it for. That's getting a bit towards the hard end of what you need to be doing for your AS, but it gives you a little insight in how proofs can develop and so on.